Uh, Thank you so much, Peter, and apologies everyone for missing the start of this recording. I appreciate the reminder and I might forget again, so please do let me know if I forget recording. What we were just going through for the recording very, very briefly is a few questions and answers. We've only just started, but we've just started talking about transforming time series. And the main reason we want to transform a time series is to stabilize the variance in the data set. So we talked about multiplicative seasonality yesterday when we had this increasing variance, but this is difficult to model. So we want to apply some transformation, and there's lots of options for this in order to simplify the patterns into a nice additive one, like so. See how the variance is now constant? And there's a few options that we have for this function. You can try the square root, perhaps the cubed root is a bit stronger, or even the logarithm. So there's lots of different options that you can plot your data with. So maybe you have y on the left, and then log of the y is on the right, and it's much simpler for modeling. Okay, so back to where we were before I started the recording, is to look at this Australian retail data set. And you can see from this time series, what patterns do we have in the data? We saw this yesterday. Does it have trend, seasonality? If it has seasonality, is it additive or multiplicative? Tell me something about this data set. And while you work on that, there's a few questions to answer. The first is a question or a confirmation. Do we need to perform various transformations until the appropriate one is obtained? That's right. So you can use different transformations, but the overall goal is to make the pattern as simple as possible. We want to make the variance stable. And that often involves trying a few different transformations that we'll see shortly. To stabilize the variance for multiplicative seasonality only, this isn't just for seasonality, but most of the time it is for multiplicative seasonality. If my data set just had a trend, but my trend was curving upwards, this is a multiplicative trend, and we can simplify this using a linear trend. So if I apply a log transformation or a square root in order to make this pattern simpler, that's also good. So it's not just for seasonality, but most of the time we use this for seasonality. Okay, looks like most people in the chat have got the right idea. This has trend and multiplicative seasonality. A few of you just wrote multiplicative seasonality, which is correct, but of course this data set has a trend as well. You can see the data is generally increasing, but the trend isn't increasing linearly. See how I've drawn a straight line there and it doesn't match the data exactly? The trend here has a slight curve to it. So this has a increasing trend as well. Okay, let's have a look at this in R. So remember, when you get started with R, you need to load in the FPP3 package. This will give you access to all of the data sets and all of the functions that we'll be using this week, and the functions that you'll be using for forecasting after this week, of course, as well. So this food time series is a monthly time series of total retail turnover in Australia. So you can see that I've filtered out the industry to only be food retailing, but there's several different states in Australia. There's 8 different places where we have data on food retailing. But I just want to see the total food retailing. So I'm going to add up all of the turnovers into a total food retailing turnover for Australia. Now, using what we saw last week, we could, of course, plot this data. And that's exactly what we saw in the slides before. We have a slight upward trend, or a strong upward trend, and we have this multiplicative seasonal shape. See the growing variance? Now, there was another related question here. I notice you use interchangeably the Magritte pipe, which is with the percentages, and the native pipe, which is with the vertical bar. Now, I've switched over to start using the vertical bar because I'm now using R version 4.4. Any version of 4.1 or later has access to this vertical bar. If you have versions before 4.1, you can use the Margarita pipe. For our purposes, they're identical. So you can use either depending on what you prefer. Thanks for the question. Okay, so to stabilize this time series, we can try some of these transformations that we saw on the slide. So let's start with a square root transformation. In R, you use the sqrt function to transform the data. So I'm just going to plot the square root of turnover. And immediately you can see that this is simpler. We don't really have a curved trend anymore. It looks nice and straight. And that's already going to be much simpler for producing forecasts. However, you can still see that the variance is a bit small at the start of the time series when the level is low. So at the small values, it's still a bit too small variation. But at the large values, when square root of turnover is 100, the variation is still larger. So we need a stronger transformation in order to stabilize the variance. What's a stronger transformation than a square root? Yeah, a few people are suggesting log. Let's try the log transformation. And the log transformation looks pretty good. You can see that the variation in the time series when the data is low is similar to the variation in the time series when the data is high. You can see how we have a constant band of variability throughout the entire data set now. So because the variation seems constant, that's exactly right, Jose, this gets our tick of approval. So the log transformation is what we want. But you can see that the trend here is no longer a straight line. It has a curve the other direction now. So this transformation is just right for the seasonality, but it's too strong for the trend. The square root transformation was perfect for the trend. You can see this nice straight line, but the seasonality was not strong enough. So here we need to make a decision. Do we want a simple trend or a simple seasonality when it comes to modeling? And almost always we choose a simple seasonality. That's because the seasonal part of the model is much harder to model and estimate and forecast than the trend. It's much easier to produce a forecast with a curved line for trend than it is to produce a forecast for a growing seasonality. So we're going to use the log transformation for this data set. Okay, there's a few questions here. The first is, how do you know that a time series dataset requires transformation before forecasting? This is a question that we'll be looking at more in future weeks when we do modeling. But almost always when the data has changing variation, so you can see the variance is small here and large at the end, then you would want to transform the data. If your data set looked like this, where you had a similar variance throughout the entire data set, or even like this with the log transformation, if your data set started looking like this, there's no need to transform the data. We want to convert whatever data set we have to have a constant, stable variance. Another question here, what may be the goal of a square root transformation? A square root transformation has the same goal as a log transformation and a cube root transformation. The goal here is to simplify the variance for modeling. We want a constant variance for the entire dataset. And in fact, our models will often assume that the variance is constant. Okay, a few more good questions coming in. Is there a limit data to get before using transformation? I'm not quite sure I understand this question. Is there a limit data? But you'll use a transformation whenever you need to stabilize the variance. There are, of course, some problems with certain ranges of values. You can't take the square root of a negative number, for example. You can't take the log of a negative number. So a lot of these transformations will require the data to be positive. But most of the time in time series, our data is always positive, and this doesn't cause a problem. Correct me if I misunderstood your question. Lastly, is it possible to plot the data with increasing trend and with no changing variance? Yeah, that's also possible. We saw that in the previous day. So let me bring the plotting slides up from yesterday. So this is an example of additive seasonality. So here we have an increasing trend, and the variance is constant. See that range of values doesn't change? Whereas more often, with real data, you'll have this increasing variance. And in this case, you want to do a transformation, perhaps a log. Okay, so follow up on this question about the limit. If the limit's about the quantity of data, there's no limit in terms of how much data can be transformed. You can have millions of observations and transform it. Are there statistics that indicate a variance besides a review of the plot? There is, and we'll look at that. I'll remember your question, and I'll get back to you when we talk about that. There's a specials function that we can use to understand the variance of the variance, how the variance might change over time. Another question here, should we transform the data if the variance is stable? No. So if the data is already stable, like this one here, there is no need to transform the data. Whereas if your data set has a changing variance, like this one, you will need to transform the data in most cases. Can we say that the log transformation removes white noise from the time series? No. So white noise is a different problem. White noise assumes that there is no pattern, meaning there's no change in variance, but also there's no change in mean. A log transformation will only simplify the variance, not the entire information that might exist in the dataset. Later, we'll be using models to remove the patterns in the dataset and into the residuals. And then hopefully, after we capture all of the information with our model, whatever is left over is nothing informative, or in other words, white noise. Okay, so with this data set, the food data set, we've decided that a log transformation is appropriate, but we can actually go even further than a log transformation. We could do an inverse transformation. See how I've just divided by turnover now? This inverse transformation is even stronger than a log. So we have the identity function, y equals y. Maybe I'll just write y. Then we have the square root, which is simply just the square root of y. Then we have the cubed root of y. Then we have the log. And you might have the inverse as well, which is the negative 1 over y. Now these are all getting stronger and stronger. And the inverse transformation is so strong that it's almost never used in practice. Almost always we'll be using the log transformation. But we have a special type of transformation which is even better than all of these. You can see here the inverse transformation is not perfect. You can see the variance is now having the opposite problem. When the data is small, the variance is large, but when the data is large, the variance is small. So you can see this isn't a good transformation because the variance is changing over time. Now, this type of transformation, the better type of transformation than choosing a log or a square root, is a Box-Cox transformation. And a Box-Cox transformation allows you to do any of the above transformations, or something very similar, equivalent to, with a continuous parameter lambda. And you can see that if lambda is equal to 0, we exactly get a log transformation. So I'm going to write lambda equals 0 is the log of y. What happens when I use lambda equals 1? Well, when lambda is equal to 1, we're using this definition. So we take the sign of y, that's if it's positive number or negative number. And this is only because we're taking the absolute value here. This is useful because if we're transforming negative numbers, this makes it possible. Now we can square root a negative number because it's no longer negative with this absolute. And then we're raising yt to the power of lambda. But what if lambda is equal to 1? So this will be yt to the power of 1, and that does nothing. So this is just yt. Then we minus 1, and then we divide by lambda, which is simply 1. And dividing by 1 does nothing, of course. So all we get when we use lambda equals 1 is yt minus 1. So our data set has just been moved down by one observation. And that does nothing to the shape of the data. And so the lambda equals 1 is approximately doing nothing. What about if lambda is equal to 0.5? Have a look at this equation. Which transformation that we saw earlier is lambda 0.5 very similar to? That's right. So this is a square root transformation. You can see that this will be the square root of yt minus 1 divided by 0.5. So in effect, this will be times 2. Now this minus 1 and times 2, that just changes the location and scale of the data. The change in shape is all happening because of this square root of y. But because we're using the sign here, which is, to answer a question in chat, this is if the data is positive or negative. It's not the sign function. It's not this. It's just if it's positive or negative. Now, the lambda equals 0.5 is equivalent to a square root, but it also allows it to be a negative number. So it's even better than a square root. But what we can see is that starting with lambda equals to 1, as we go further down, we're getting a stronger transformation. So to answer another question related to this, how do we find lambda? It's very similar to what we did with the previous plots, in that if we need a stronger transformation, we use a stronger lambda. So we move lambda further away from 1. So you want to look at the plot and see when the variance looks stable. Another question is, what is the log function? Is it in base 10? So for this, we're using the default log function in R. And if you look up the help file for log, which you can do with $log, you'll see that there's a few options. By default, log is the natural log. You can see the base is the exponent of 1, e. Whereas if you wanted log 10, you could use the log 10 function. And log 10 is a valid transformation as well. You could try a log 10 transformation and see if that works well for your data. In this case, it's very similar to the log function, the natural log. Okay, I think I've answered everyone's questions. So you can see that relationship that I just wrote out before. Lambda equals 1 does nothing. Lambda equals 0 is a log. And if you do lambda equals -1, you can see quite quickly this will be yt to the power of -1. So this is the inverse function. Now there's a little animation here that I'm not sure I can play, but we'll show this interactively. So let's move across back to R. And we'll try to identify the value of lambda for this data set. So in R, we use the autoplot function again, but now instead of a square root or a log transformation, I'm going to use a Box-Cox transformation. And to use it, we need to specify two things. First, the response variable, turnover, and then lambda. So I'm going to start with lambda equal to 1, and we can see this effectively has done nothing to what my data originally looked like. Then we might try lambda equals 0.5, something very similar to the square root transformation. Does this need a stronger transformation? Is it just right? Or do we need a weaker transformation? Should lambda be smaller? Lambda less than 0.5? Stronger transformation? Or lambda equals 0.5, it's just right, keep it. Or lambda greater than 0.5, transformation was too strong. Looking at this plot, can you see a changing variance? And in what way is it changing? Okay, very good. So you can see that the variance is increasing. And when the variance is increasing like this, when the variance is proportional to the y-axis, exactly what was mentioned here, I really like this answer. Variation is higher with larger numbers. When you have this problem, your transformation needs to be stronger. So I'm going to use a lambda less than 0.5. Does anyone want to guess? Let's suggest, I'll take the first suggestion. Pick a number less than 0.5. Could be any number. 0.25, let's try that. And then we repeat the process. So here is 0.25, and I want you to put in the chat stronger or weaker or perfect. What do you think about this transformation? Do we need to change it? Okay, most people are saying a little bit stronger, a couple of people saying weaker and we need to change it. I think most of you are right. This one is almost there. We're so close, so we don't need to change it much, but the variance is still a little bit smaller at the start when the values are lower than at the end when the values are higher. So if this is too weak, how would we make it stronger? Suggest another number. 0.15. Very good. I still think this one is a little bit too weak. So let's go even closer to 0. Maybe 0.05. And now it's looking really good. You can see the variance at the start, when the values are small, is practically the same as the variance at the end. I've not drawn that very well, but visually I hope you can see that this is very close. Now the good thing about this is that as long as you're close, it's good enough. The model is not very sensitive to slight changes in variation. Of course, the closer to perfection, the better. But when it comes to forecasting, the difference between 0.05 and exactly 0 using a log transformation is not very much. And so as long as you're close with this value of lambda, that's close enough. So I hope that helped you understand how to identify a value of lambda. But there's a trick here as well. We can do this even easier. And as Brian asks, is there a way to get the best lambda without making several guesses? And there is. And that method is using Guerrero's method. Guerrero's method takes your time series and it splits it up into sections. So maybe we looked at the first section here, and it calculates the variance. What is the variance of this? Maybe the variance is equal to 1. And then it looks at another section of the data. Here the variance might be equal to 2. And then finally the last section, the variance is equal to 3. So this is Guerrero's method. So we start at, say, lambda equals 1, and we can see statistically that the variance in each of these sections is changing over time. And then we use computer optimization, and then maybe we try lambda equals 0.5. This is all happening automatically. And when I use lambda equals 0.5, just redraw this red line, like so. So when I use lambda equals 0.5, make that a bit more obvious. Maybe it's a bit better now. Maybe my variance is 1 at the start, 1.5 in the middle, and 2 at the end. So you can see the change in variance is smaller. And then lastly, if I do lambda equals to 0, which happens to be the right one for this data set that I'm making up, now my data set has the same variance in each of these sections. Variance 1, 1, 1. And so Guerrero's method has found the answer, and it will return the value lambda equals 0. And we can use this on any data set, and most of the time this works really well. You do have to check, you can check the values of Guerrero's method, but let's try this out for this data set. There's a few questions. I'll get to those questions later. So to calculate Guerrero's method, we use the features function, which we'll be looking at a lot today, and we give it the variable we want to calculate the best possible lambda for. And then lastly, we tell it what function we're going to use. In this case, it's Guerrero's method. And you can see it's gone away and calculated the best value of lambda, the optimal value based on the variance of the variance. Lambda is equal to 0.09. And if I plot that optimal value, 0.0895, you can see it's very close to what we found experimenting with different values of lambda. The variance is now stable across the entire time series. And in fact, you can do this in one step if you like. You can use Guerrero inside this function. So we use boxcux of turnover, with the optimal value of Guerrero for the turnover variable. And that will give you the exact same result. Okay, so the few questions. That question above, is there statistics to calculate or look at the variance? Guerrero's method is what I would use to find the best lambda, which is using the variance of the variance in those chunks that I was talking about. Is overfitting an issue to worry about with variance stabilization? No, not really. In this case, there's only one parameter available, so it's not possible to overfit here. Overfitting usually happens when you use too many parameters in a model. How can I get access to the files and resources to practice and follow along? I'll put the link in the chat. You can find everything that you need on this website here, the AFRICAST workshop website. And if you go to the top here, you can download either the entire website, everything. You can download all of the slides or all of the exercises and lab sessions that you'll be working with your mentor. The main thing is to install the required software, which you can do on any version of R, and use library FAP3 to follow along. Okay, so because we need a stronger transformation, lambda should always be as low as possible. That's not exactly right. Let me keep that up here. Now, if I tried to make lambda as small as possible, what if I made it negative 0.5? Well, that's not as good as it could be. What if I made it negative 1? Now it's getting worse. Negative 2. If I made it as small as possible, you can see it doesn't always give me the best results. The best results is the transformation which gives you the most constant variance. In this case, it's 0.9. 0.09, I should say. This gives a very good result. So it'll change depending on the data set and how strong the multiplicative patterns are. Is it possible to generate a new variable of the Guerrero value of each observation? So the Guerrero value is, the Guerrero value is a summary statistic of the data. So you might have an entire time series, 100 observations. Guerrero is just one number that describes that entire time series. So you can add a new variable with the Box-Cox transformed Guerrero using dplyr. Food mutate turnover Box-Cox equals the transform turnover. Now I've got my original turnover and my transformed turnover, but we never really do this because we're not interested in the transformed data. This is just a modeling step to simplify the data. When we're forecasting, we want forecasts of turnover, not Box-Cox transformed turnover. So usually we don't transform the data in the data set itself. We usually just change it when we're plotting it or modeling it, that we'll see in future weeks. How can we output the lambda value used by Guerrero? Is it important to know? Yes, you can use the features function that we saw earlier, this one here, which is also shown in the slides. Food features turnover with the Guerrero feature. And when you use this function, you can see the value of lambda shown here. Now, it would be even better if you wanted to add the label here, plus y label, Box-Cox transformed turnover lambda equals 0.895. Just so that the plot is very clear about what was being shown in the data. The range of lambda is from 1 to negative infinity. Final question. The value of lambda could be anything. So there's no limit on what lambda could be. It could be 0, which gives you a log transformation, or it could be not 0, which could be positive 2, could be negative 2, could be 100, you'd never use something like that. It's far too strong. Or negative 863. You could use any value that will stabilize the variance, but almost always you'll find that the best values are between 0 and 1. Very rarely would you need a value of lambda outside this range, but it is possible. To answer your question, Gabrielle, if we won't be working with Box-Cox transform data, what is the purpose of the transformation? We use the Box-Cox transformation as a preparation step. So we actually do use it a lot for modeling, but we never show it in our final results because we're more interested in forecasting final turnover, overall turnover. But to do this, for the modeling, we use transformed variables instead. And then we undo the transformation at the end. We'll be seeing this more when we do the modeling. Actually, we'll be seeing it in the second session today as well, when we do decomposition. Okay, so here's some summary on transformations. Usually, you don't need to do any transformation. And the less that you do, the easier it is to explain. So often we want to do a simple transformation like a log transformation. Now there's a few other facts here. If you have positive values, using a log transformation is a good idea to enforce your forecast to be positive. That way you don't have your data all being positive and then your intervals go negative. Using a log transformation, because we back transform, we undo that transformation at the end, will force all of the values from our forecasts to be positive. So you can see at the end here, transformations must be reversed to get forecasts on the original scale. And this is what we care about. But fortunately for us, we'll see in future weeks, this is done automatically by Fable. Now, there are a few other types of transformations that you can consider. This is out of the scope for today, but it's worth having a read through if you're interested. Chapter 3 of the book. I'll put this in the chat. Transformations and adjustments. You can also consider adjusting by the calendar. So the days in month is a very common adjustment to make. Maybe because there's only 28 days in February, this year 29, there's going to be less sales simply because there's less time in this month. So a calendar adjustment helps simplify seasonal patterns. You can also consider population adjustments. If you're comparing different countries, dividing by population is a good idea to get per capita comparisons. Inflation, if you're working with monetary values over time, which is what we're doing here with turnover. So it'd be a good idea to divide this by CPI, and there's some examples in the book. And then what we're focused on today is mathematical transformations, which is excellent because you don't need to use any additional information in order to do the transformation. It's purely math. And there's another example here that you can play around with in the book, trying different values of lambda to get the optimal value to stabilize the variance. So here is the link to that if you wanted to read more about other types of transformations after today. Okay, next we want to look at adjusting time series, which I guess we're actually going to talk about per capita adjustments. So you can see there's a very subtle difference here between these two plots, but it is changing the shape of the data subtly. See how this line doesn't look exactly the same between these two plots? But what's most useful with this type of adjustment, a per capita adjustment, is the scale of the data. A GDP of 1.5 trillion, I think this is not very informative because it is usually proportionate to population. And you can see a GDP of 60,000 is a much easier to understand number that on average people in Australia produce 60,000 Australian dollars worth of product each year. Inflation adjustments, this is the example in the book. The code is a little bit complicated and I'm not going to go into the details here, but essentially we're combining two different data sets together. The first being the retail data set that we were looking at for the food example before, except this time instead of food, we're looking at newspapers. And then we're also looking at the global economy data set that we saw yesterday. And then we're joining these two data sets together with a left join to calculate the adjusted turnover, which is turnover divided by CPI. And then the rest of this code here is simply plotting the data. So most of this code is building on tidyverse tools. You can see there's a lot of use of dplyr and ggplot and even some tidyr there. So if that's a bit intimidating for you, you can learn more about those tools on the Learn R website here. But you can see when we adjust turnover for inflation, we get a very different pattern. Turnover, the original data, was increasing in trend until 2010, until it started decreasing. But most of this increase was actually because of inflation. And by dividing by inflation, removing it as one of the patterns in this data set, we get a simpler pattern. Now it's actually been decreasing from 1985, and after the year 2010, it's been decreasing even faster. So this tells a more accurate story for what is actually happening in the print media industry. Okay, the next big topic. Any other questions about transformations before we look at our first model for the week? There's a good question here. Is Box-Cox transformation the same as scaling of variables? It's related, but not exactly. Scaling of variables is normally a multiplication of y. So it might be 2 times y. And what this will do is that the line will look very similar. 2 times 2 is, say, 4. 2 times 6 is 12. 6 here, 12 here, 2 here, 4 here. Essentially, we will get the same line with a stronger trend, I should say. Whereas transforming the data with a log of y will change the shape. So what this will do is stabilize the variance. Now, if you remember before when I was talking about the Box-Cox transformation, here we have scale, and this is location. Now, in terms of the modeling of the dataset, the coefficients in the model, these two don't do anything practical to the model. It'll just update the coefficients, and the forecast will be identical. If you scale it by a constant or shift it up or down by a constant value, there's no change to the model. All of the change in the shape of the data is happening here. Simplify the data. So this power transformation, the power of lambda, is what's doing all of the work to make our data simpler for modeling. So when we talk about scale, it's not exactly the same as the transformations we've been looking at, but it's very close. Thanks for the question. Okay, let's move on to the next topic, time series decomposition. Now, we saw earlier, when we thought about additive and multiplicative decompositions, that we had the seasonality added to the trend. And then we also considered a multiplicative decomposition. Maybe I don't have a slide for that. Okay, I do have a slide, but it's not the way I wanted to show it. I'll just write it here. So we also considered a multiplicative decomposition, where we had yt equals to st times tt. And then here I've also added the remainder term, because now we're using a model. There's going to be something that the model wasn't able to capture, and we call this the remainder. It's whatever is left over. And for a multiplicative model, this would be also multiplied to the trend. And if we use a model that understands seasonality and trend separately, then we can separate the components. We can take a single line of our data and split it up into the trend, seasonality, and remainder. And this process is known as decomposition. And this is a very common task used for statistical bureaus when reporting figures. Often when making decisions, remember the whole purpose of making forecasts is to make good decisions. Often it's a good idea to remove the seasonality entirely. When we remove the seasonality, all we're left with is the trend and the remainder. So if I remove seasonality from my model, then I just have trend and remainder, and this will look a lot simpler, just a straight line. And when I forecast from that, we can see, without seeing the changes from day to day or month to month, what the overall growth of the data is showing. And this is really important and useful for decision making. So let's see how we can do decomposition. There's several different ways that you can decompose data. The one that we're going to be looking at is perhaps the best one, the STL decomposition. It uses a localized regression model. Has anyone heard of a LOES model? Local regression. Bahman, just letting you know that that link that you sent in the chat was only to hosts, so I'll send that again to everyone. I've made that mistake quite a lot. Okay, so at least one person hasn't seen a localized regression. Who's seen a regression before? If I've got a bunch of dots and I did a regression through this, have you seen that a regression might do something like this? Just a y equals x regression. So we could use time on the x-axis. You've probably seen this before. So if I did a straight line trend, or in this case a straight line regression through the data, this is a good estimate of my trend component. But what if I had seasonality? If I had my seasonality, then hopefully my model can estimate it well. So this is now trend plus seasonality. See how it's an additive relationship that I've drawn? Now there's a question before, can we say the remainder is like an error? Yes, it's very similar. It's going to be the difference between what the model was able to capture. So you've all seen regression before, it seems, which is excellent. Let me move that across. Done. Very good. And another question, is the remainder the same as randomness? Not quite. It's whatever the model didn't capture. So hopefully the model was able to capture everything, but if it hasn't and it left in some other patterns like seasonality, it's not guaranteed to be random. Okay, so this is a regression model. It takes all of the data in one go and it estimates a model. You've all seen that before, I hope. A localized regression splits the data up into very small chunks. So let me show you this with a different example, different data set. What if my data set started increasing, flattened out, decreasing? What would a regression model do on this data? It would draw a line straight through the middle. And that's not a very good fit of this data because a time series, the patterns in a time series can change over time. So what a localized regression does, instead of using the entire data set, it just uses one small section, very similar to what Guerrero's method did to find the variance. And then it estimates a trend here. And that's a very good fit of the data. And then it moves the window across a little bit. And it estimates a trend again. And then it moves it across once more. And now I get a flat trend. When I do a regression model only on this area of the data, I get a very different trend from what I had before. So I keep estimating these windows. And suddenly, using a very simple model like regression, I can follow the data very closely, even though my trend has been changing over time. And the size of these sections of data is known as the window. You can think of for each window of the data, we're estimating a regression model. Any questions with a localized regression model? What is the assumption given to the remainder of the model? This follows all the assumptions of a localized regression, and I believe it assumes normality under the windows. So yes, there is some normality assumptions in this type of model. A question here, what is the hypothesis for a localized regression model? There is no hypothesis in this case. We're just trying to estimate the patterns in the data. Is there a specific way to determine the size of the window? That's a great question, and we'll see that when we try different examples in the code with real data. Okay, but there are some caveats with this method. A regression model is maybe beta naught, that's my intercept, plus beta 1t, my x variable, plus my residuals, which I'll use epsilon to describe. So this regression model, which is the same model that we're using in each of these sections, each of these windows, you'll notice that it's additive. So one of the big downsides of this model is that it can only work with additive data. Only additive. Now you might think that's a huge problem because a lot of the data we've been seeing so far has this multiplicative pattern. But of course, we've just learned the answer. We've just learned a trick to make our data simpler so that we can use an STL model. And that, of course, is to use a log or a Box-Cox transformation in order to convert my multiplicative pattern into an additive pattern. So we need to put both of these ideas together in order to decompose the data. Let's try that out. So there's an example in the slides here, but I wanted to show you a different example. Let's use the food data set that we were looking at before. So if I use food and I autoplot the log of turnover. Now I'm just going to use a log transformation for simplicity. The log transformation has an additive pattern. It's very close to a constant variance. And this is close enough for my STL decomposition. A regression model would work quite well for this. Now to estimate an STL model, we're going to use a new function, the model function. And the model function accepts a model specification. In this case, we're going to use an STL decomposition on the employed variable. Now you'll have to look at this code very closely to get the syntax correct. We take our data set and then we pipe this into the model function. Now, what models are we going to use on this data set? We're going to use an STL model on the employed variable. Or in this case, we're looking at food turnover. So we take food, model the data set using an STL decomposition on the log of turnover. Remember the transformation. Because we have multiplicative data, we need to make the data additive using an appropriate transformation. In this case, we're using the log transformation because it looks really good when we did the first part of the day. And what I get from this is a MABLE, a model table. Now, a model table in this first little cell here contains my model for the data. And this works when you have multiple time series with those key variables we saw yesterday. And it also works if we have multiple models, which we'll be seeing in future days. So we've estimated an STL model, and we can get the decomposition for that using another function. And that function is components. So if I pipe this model into the components function, you can see I now get a table. And this is a decomposition table. Now, what this decomposition table has done, it works very similar to a Sybil, where I had the monthly data, but it also knows how the data was split up. We're using the log of turnover is equal to the trend plus the seasonality plus the remainder. Remember, this is y equals t plus s plus r. But really what we're working with is the log of y, because y itself is multiplicative. Now, the most important thing from today, from this session, is to plot it. So if I use the autoplot function, just like we did for making a time plot, I will get a plot for each of the components in the model. You can see I get a plot of the original data. This is YT. I get a plot of the trend. And look how simple this trend looks now. There's no random. That's all in the remainder component. There's no seasonality. That's all in the seasonality component. All that I'm left with here is the trend. The seasonality is also easier to look at. It's in the seasonal component. And the remainder is all of the random stuff left over. Now, because I've used a log transformation, you can see some changing variance. If I used a better transformation like 0.09, like we found with Guerrero's method, this would look a little bit better. We assume and we hope that the variance is constant. Now, there's a few more things that we can do with this. The first is to plot the seasonality a little bit better. So remember last session when we used the ggseason function and we looked at turnover, for example? We could see that all of the data tends to increase in December. So the peak is in December. But look how spread out these values are. This is because of the trend. So something we can do that's really useful with decompositions is to take those components from the code we had before and then use the season plot on the seasonal components. So you can see the season year column is just a column of this data set, and I can plot it just like any other variable. I can auto plot it, and I get my seasonality, or even better, I can look at the ggseason plot. And now I can see the seasonality without the trend in the way, because I've removed the trend using an STL decomposition. Now this is a very cool tool and very easy to see that February has the minimum and December has the maximum. Now why does February have the minimum? This is probably because there's 28 days. So there's less time to sell food. December sells more because everyone is having a feast. Everyone is eating a lot for their holiday periods and celebrating, so people tend to spend a lot more on food in December. Now, another thing people like to do is to plot the seasonally adjusted data. So in this case, I'm just plotting the trend without the remainder, but often we'll plot the seasonally adjusted data as well. And that's shown here. So you can see in gray, I have the original data with the seasonality, but the seasonality can be a bit hard to see the true underlying pattern that's relevant for decision making. So there's another column of this data set, season adjust, which I can plot as well. Season auto plot, season adjust. So here I have a trend line increasing, but I also have the random variation, which is useful to understand how predictable the dataset is. In this case, we have very little random noise, and so it is very easy to make a good forecast from this. So this is often the very useful plot for making decisions. And if I didn't want to see the components of trend and remainder, which are combined additively to give the seasonality, the adjusted seasonality, sorry, the seasonally adjusted data, removing the seasonality from the data, I can convert it back into a Sybil. And then I just get my original time plot that we saw yesterday. Now, this seasonally adjusted process is quite simple. If I have yt equals s plus t plus r, then to seasonally adjust the data, all I need to do is move the s over to the other side. So I have yt minus st equals trend plus remainder. And this will give me my seasonally adjusted data. Of course, if I had multiplicative patterns, I can divide by st as well. Okay, there was a question before about the window. Now, the window controls how much data is in each of the localized regression models. A big window, like infinite or periodic is another word for that, is making sure that the seasonality does not change over time. So if I copy this decomposition, I'll put this in the chat as well, if anyone wanted to follow along and catch up. You can see here in the seasonal component, the seasonality is changing a little bit. See how it's dropping down a bit in the peaks? December sales of food is decreasing in the 2000s. I can force that component to have a constant seasonality by setting the seasonal window to be infinite. And just like you use the lm function in R with the tilde, you've hopefully seen this before, you can specify things about the STL model using the tilde. So on the left of the model, we have what we're forecasting, in this case turnover. And then on the right, we have some information about how we're forecasting it. In this case, we're using a seasonality with an infinite window, meaning that there is only one regression model happening for the entire data set for the seasonal component. If I set this window to be really small, maybe 5 years, you can see that the seasonality can change very quickly. See how much it's changing from year to year? Now the goal here with setting the seasonal window is to choose a value that is large enough so that it's nice and smooth. Remember, the assumption is that seasonality is consistent and predictable. It shouldn't change very quickly. So a seasonal window of 5 is far too small. Something like 13, for this particular example, is better. You can see how the seasonal component is now very consistent. It is able to change a little bit, but not much. Now you can do the same for the trend component as well. You can set the trend window equals to infinite, and we add these components together. Now, of course, if I have an infinite trend and I'm estimating a regression model, all I get is a straight line. But that's not realistic. The real data isn't a straight line. It has a slight curve. And so here, the window is too large. If we try something really small, like 3, you can see that it has essentially absorbed a lot of the errors. Now you might see the remainder component and see 0 errors and think, we've got a good model. But that's not the purpose of a decomposition. We don't want 0 errors. This is sort of like overfitting. In this case, the trend is capturing the remainder as well, and that's not what we want. So perhaps here for a window of 9, you can see it's able to capture little bumps. So it flattened out a little bit there when the data flattened out, but generally it's increasing with a curve. So you play around with these windows until you get a sufficiently smooth line which captures all of the patterns for trend, seasonality, and remainder correctly in the right category. A few questions here. Is window the same as bandwidth? It's very similar for kernel density estimation bandwidths or density bandwidths. Yeah, you can think of them as being very, very similar. Oh, lots of questions. Does remainder refer to residuals? Yes, it's in this case the residuals of the localized regression model. And the season adjust function isn't a function, it's something that exists in the data. There's a season adjust column here, and it calculates the difference, the data without the seasonality, which is shown here. So it just calculates y minus seasonality. Very informative. How do I add the red color on the table? I'm not sure what you mean. If you're referring to the lines that I'm doing, that's just some software that I have on my computer to write on the screen. If I use log of y in the model, does that mean that lambda is equal to 0? Yes, that's exactly right. You could see in the up the front here, the definition of the boxcox, when lambda is equal to 0, it's exactly the same as a log transformation. So you can use either. Multiplicative models can't be used on time series with zero values. Transformation strategies today. How can we deal with zero values and transformations? There's a nice trick to this for STL decompositions. You often like to use the log plus 1 transformation if you have zeros. So if we do log of y plus 1, this gets around the problem of y having zeros. But it still, for most of the shape, looks and works like a log transformation. And lastly, this question, I know I've been waiting on this one for a while. The data here was transformed because the CPI was changing over time as well. So because CPI was not constant, therefore the shape of the data was changing proportional to CPI. Okay, so there's a lot we can do with STL decomposition. The most important thing to consider with this is choosing the appropriate window. So you can specify the trend window for controlling the wiggliness of the trend, and the seasonal window for controlling the seasonal variation. And you want to make sure that the seasonal plot, the decomposition plot, contains the components that they say they contain. So the trend should contain a trend and not anything more. In this case, the trend contains the remainder as well. So this is bad. The seasonality should be really smooth because by definition, seasonality should be consistent. And very often we use an infinite window or a periodic window for our seasonality. If you have some outliers, you can also consider using robust equals true, which will reduce the effect of outliers in the model. So there's a plot on the retail employment in the United States, and you can see this is a good decomposition. The trend follows the data closely, the seasonality looks consistent, and the remainder looks pretty random, and it has a constant variance. So here is how the STL decomposition model works. And you can see the window and bandwidth, these terms are used interchangeably. Now we can do this with multiple time series. We looked at the holidays data set yesterday. And you can see now we get multiple decompositions from this data set. Now this is really powerful for looking at a sub-series plot. Remember when we yesterday looked at changes in seasonality? Using a decomposition can remove the trend and make it much easier to see if there's any differences. In this case, ACT, in Q4, seasonality has been decreasing, or travel to ACT for holidays has been decreasing, while in Q1 it's been increasing. Now, this also works for multiplicative seasonality. We saw the Victorian electricity data set yesterday. And if you simply model this using the STL decomposition, you can get a separation of the annual seasonal pattern, weekly seasonal pattern, and daily seasonal pattern. And in fact, this is half-hourly data, so it's also pulled out an hourly seasonal pattern, which is just on, off, because it's every half hour. There's only 2 observations in each season. And you can see this has decomposed the components quite well. What it hasn't been able to do is in the remainder, you can see there's big peaks at the start of each year. Does anyone remember from yesterday what this is probably doing? Why we have so much randomness at certain times of the year? The seasonal component for the year has tried to pick some of this up, but it's not able to do all of it. And remember, we're talking about temperature. So demand is strongly related to temperature, but in this model, we haven't been able to use temperature at all. So what's happening in the remainder is when we have a heat wave, and heat waves are very unpredictable. So if we had temperature in the model, we would get a much better, more random looking remainder term. Okay, I'm going to finish this first session with a word of warning about the ABS. This is the Australian Bureau of Statistics, and they were doing a decomposition on employment data. So you can see that this news story was quite important because a lot of businesses were very concerned. A lot of politicians were very worried about the ABS reporting of this figure, because what happened was that usually employment goes up very smoothly with some very slight seasonality, but right at the end of the data, there was this big drop. You can see this in August. Normally there's a drop in August, but in 2014, there was no drop. And this surprised a lot of people, and people made some investments, people lost money as a result of this. You can see the outlier here. This is the mistake. And the reason why this mistake happened was because the way they collected their data, remember from the very first thing we looked at yesterday, in that workflow, gathering data and information, what happened in this story is that the government changed the way they collected data. They asked a different question. And because of that, people were now answering truthfully. Because if they answered earlier, in 2013, in any of these years where it behaved normally, if they answered yes to a question, they had to answer another 10 questions. Whereas in 2014, they changed the survey so that they removed that question and suddenly everyone started answering truthfully. And so the employment figures were actually correct now. There wasn't this artificial decrease that we normally have. So the data is better quality now, and that's usually a good thing. But when the decomposition was made, what happened was that it inflated that value for August. And it inflated it so much that it made the news, and people got very concerned with the results and started losing trust in the analysis. So it's a good idea, as we did yesterday, to always plot your data from the raw data to the finished models and forecasts in order to look for anything strange before publishing your results. Because this seasonally adjusted data is really important for decision making. And when you're at the end of the data here making a decision and you see some strange values like this, you're going to be asking some questions. Why did employment increase so much in this month, suddenly to decrease immediately after? Whereas in the past, it was very stable. So as a result, they implemented a new adjustment. They improved their seasonal decomposition to fix the problem and added some extra checks in order to prevent it happening in the future. But the overall message with this is to be very careful with your modeling, and we'll give you some extra tricks throughout the rest of the week in order to make sure that your forecasts aren't missing any information that they might need to consider. Okay, with that, we're going to take a 10-minute break. If you have any questions, feel free to ask them in the chat. I'll work through these during the break. And next, we're going to look at features. We saw a little bit about this with Guerrero's method, and we'll be seeing more in the next session. Okay, welcome back to the second session of day 2. So for the second session, we'll be looking at time series features some more. So you can find this on the schedule. So look at computing and visualizing time series features, and we'll do this for another hour and a half. And then you've got an exciting day ahead tomorrow with both Bahman and I. We'll be looking at time series forecasting. Okay, so in the previous session, we saw the STL decomposition model. But one of the other really useful things that you can get from the STL decomposition, in addition to the decompositions we were just looking at, is features. And features allows you to summarize all of these patterns that we were looking at yesterday, like trend and seasonality, into a single number. Very similar to what we saw in the previous session, where we summarized the data set into Guerrero's number. What is the optimal Box-Cox transformation lambda value? That's one example of a feature, and if you recall, we used the feature function in order to calculate it. It was somewhere here. There it is. So we used the features function in order to calculate the Guerrero feature on the dataset turnover column. So the STL decomposition, if you recall from the previous session, decomposes the data into the trend plus the seasonality plus the remainder. It's an additive decomposition. But because we have separately the trend, seasonality, and remainder in an additive format, we can calculate some useful summary statistics of the data, including the strength of the seasonality and the strength of the trend. And these are numbers between 0 and 1, where 1 is strong seasonality and strong trend, and 0 is no trend or no seasonality. And the calculation is quite simple. We have 1 minus the error or remainder divided by the seasonality plus the remainder. So what this means is that if the remainder is 0, then the seasonal strength is 1. But always you'll have some sort of remainder in a good decomposition. But the amount that we subtract is going to get smaller if the seasonal variance is large. So if the seasonal variation is large, this number will be closer to 1. The remainder here is sort of for scaling between 0 and 1. The same is said for the trend. Instead of seasonality, we now have trend, and it works very similarly. Okay, let's return to the food data set. In order to calculate these features, we again use the features function on the turnover variable, and we want to calculate features STL. And what this does is it estimates an STL decomposition on the data, and then it computes these statistics. And it also computes a few more. In this case, it's calculated the trend strength to be 1. So this suggests that we have an incredibly strong trend in the data. It also calculates the seasonal strength. In this case, it's also very close to 1, suggesting we have a strong seasonality. Now there's some other statistics that are calculated here, including the peak seasonality and the minimum seasonality. We could of course see that using a season plot. It also calculates how straight the lines are, how linear the data is, or how curved the data is, how much the randomness is having an effect on the data. So there's lots of things involved with an STL decomposition, and the most interpretable, most interesting ones here is the strength of the trend and the strength of the seasonality. Now that's not so useful because we could of course plot the data and see for ourselves just how strong the trend and seasonality was. But what if I looked at the tourism data set? We saw this one yesterday as well. When we're looking at the key variables, we saw that this data set had 304 different time series in it. And so if I tried to plot it, and I'm probably making a mistake by trying to do this, and it's not going to stop me, it's just going to give me something useless. If I plot all of the tourist data all at once, can I understand any of the patterns that exist in this data set? Definitely not. So you can see what I get here is a whole bunch of guides telling me what is being plotted when what color is corresponding to the lines, but there's so many different time series that I can't even see the data. So if I remove the guide for the color, this is what I get. This is my data when I plot all of the tourism data all at once. Now I can't see anything useful in this time series, and most of the time series has very small counts, and it's just one big mess on my screen. But what I can do when I'm working with large numbers of time series, like this one, 304 here, even if you had hundreds of thousands, this also works, is that you can use features to summarize the patterns in the data. So I'll use the same code as above. I will use features on the trips variable and use an STL decomposition. And now what I get is that I have summarized across all of time. So each of these lines on the right has been reduced into a single dot on a single row of this data set. So now instead of 550,000 observations over time, I've got 304 summary statistics of the patterns of the data. And you can see how the trend strength and the seasonal strength is different for each time series. In this case, the holidays in Adelaide have a moderate trend, but it has a very strong seasonality, which makes sense. People often go to a holiday at specific times of the year, whereas for visiting friends and relatives, it is less seasonal. People often go regardless of time of year. You can also see for business travel here, it's even less seasonal. So this gives us a quick overview of the patterns of the data without looking at each time series one by one. And I can, of course, plot this. There's nothing about time series here now that I've summarized it. I can do a scatter plot, trend strength against seasonal strength. I'll put this code in the chat as well. And this gives us a very high-level overview of every time series in this dataset. There are some time series that don't have much trend and doesn't have much seasonality. So these time series don't have much pattern at all. And there's other time series which have very strong trend and seasonality. If I wanted to find which time series has the most seasonality, I could look at these ones, because the seasonality is closest to 1. If I wanted to see which one had the strongest trend, I could find it here. But what this is showing me is that this time series dataset has a broad range of different trends and seasonalities existing in the dataset. I can then use my key variables, such as purpose, to get an even better look. Maybe I add a color for the different purpose of why they're traveling. And now you can see in the green, see how all the green ones are higher up? And this is because it's the holiday travel, and holiday travel has a higher seasonality, a stronger seasonality. You can also see that the business trips in red are less seasonal. Most of them are down here. There's not much trend and not much seasonality. So this is a very powerful tool for getting an overview of the patterns in the time series. So that's the wrong slides. Okay, here we are. Now here's just a different layout of what I showed you before. I've added some extra code to make it look a bit nicer. I've faceted now by state. So you can see for each of the different places in Australia, what the patterns look like. And you can see Tasmania, whenever people are going for a holiday, it's a very strong seasonal pattern. All of the places in Tasmania for holiday travel is very seasonal because it's far too cold to go any other time of the year. Whereas for other reasons, and especially business regions in Tasmania, it's not seasonal at all. People go to Tasmania for work regardless of time of year. There's a question in the chat here. Could I please explain the difference between seasonalities and trends? Of course. So we saw this yesterday. That would be in the second session. So a trend was a general increase or decrease in the data. And seasonality was a fixed period of time with the same pattern. So you see this up, down, up pattern that we have. And we can combine the two. So we had an increasing trend and a seasonality here, either additively or multiplicatively. Here, the SDL decomposition is just showing you the overall strength of the trend and seasonality. So if there's a lot of trend, like in this example, see how the trend is very clearly going down? This might have a strength of 0.8. Whereas here, it doesn't go up as confidently. So because this one is a bit weaker, ignore the dashed line, this might have a strength of 0.3. So the strength indicates the overall amount of trend and seasonality compared to the randomness in the model. Okay, now what if we wanted to see which time series has the strongest seasonality and which time series has the weakest seasonality? We can use filter from dplyr in order to identify the key variables matching the maximum and minimum. So let's try that out. I'm going to take my features and save them for later. So now here's my data set of features. I've got my trend strength and my seasonal strength. If I wanted to find which region, state, and purpose had the maximum seasonality, so that's this one here, how do we find what time series this is? Well, we can filter from dplyr to find the seasonal strength that was the maximum. Seasonal strength year equals maximum seasonal strength year. There's lots of ways you could do that. There's also a fancy function called top n, which you could do top n 1 seasonal strength year, I think. Yeah, that also works as an alternative. But we can find that the maximum seasonality time series is holiday travel. That's what we expected. That's why it's green for holiday. And if you know anything about Australia, the snowy mountains is exactly what it sounds like. There's a mountain range which is very cold and it snows, and people go there for skiing. But people only go there for skiing in winter. There's no one going to these mountains for a holiday in summer. There's nothing interesting to do up there other than skiing. And so this is a very seasonal time series. So tourism, let's use this to plot that data. There's a few ways you could do this. You could, of course, filter the purpose to be holiday, the state to be New South Wales, and the region to be the Snowy Mountains. And then I've made a typo, which is very easy to do. So I've just fixed that typo. And then plot trips. So you can look at the key variables and match them up in order to find the right time series. And you can see that this is a very strong seasonality. There's that up and down pattern, and it's the strongest pattern in this time series. There's not much trend, there's not much remainder, but there is a lot of seasonality. And that's why the strength of the seasonality is so high. But there is a better way. You saw that I made a typo here with filtering. If I instead save this as tourism most seasonal, so now I have that one row data set with the most seasonality. And then I use semi-join. What semi-join does is that it keeps the rows of tourism that match the other data set. So a semi-join will do the exact same thing as the filter without needing to write out all of the key variables. And you can see I get the same data set. So let's use this pattern again, the semi-join, in order to find the most trended time series. And I'm going to use top N for this. So let's see this tourism trendy. And instead of seasonal strength year, I'm going to use trend strength. So plotting the features again. We're looking at this business travel, but we don't know what state and region this is that is so trendy. So to find the top one trend strength, we can use the top N function. You could also, of course, use filter maximum like we did before. And we can see that this is Australia's north something in West Australia. Let's make that bigger. This is Australia's northwest in Western Australia. Whoops. Bear with me. Okay, so then we can use this same semi-join technique in order to find just that time series on its own. So instead of most seasonal, we're going to look at the most trendy. So tourism trendy, auto plot, trips. And now you can see this time series has a big increase in trend in the time series at the end. I could also look at the top 10 trendy time series. Maybe I wanted to write about the most trendy places to come to. I could look at the top 10, and then here I get various business, holiday, visiting. Australia's northwest and south is very popular. The Blue Mountains, Melbourne. There's lots of different places here in the data set that are highly trended. And you can see all of these have an increasing trend or a strong trend somewhere in the data set. So this is a very powerful tool. I understand it could be a little bit complicated to think about, but especially when you're working with many time series all at the same time, being able to find the time series that are interesting is really useful. And a good way to do that is to look at the most trend and the most seasonality using an STL decomposition. So there's the Western Australia Northwest business travel, which was the most trended. And there's more than just STL features that we can calculate. We could do ACF features, but I'll take any questions now. Top N, 1, and X. The question here is, what does the 1 refer to? So perhaps I answered it by changing it to a 10, but this just tells you how many from the top you want. So if I wanted the top 3, I can use 3 there, and now I get the 3 most trendy places. And when I plot that, I only get 3 time series now. And that's right. So the trend strength here, the second argument is the weight, and this is how we've sorted the top N. So it's in order of trend strength that we're keeping the first 3 rows, the top 3 rows. Okay, another good question here. Interpretation of trend and seasonal strength, is that similar to a correlation coefficient? It is similar, but it's specific to trend and seasonality. And a correlation can be positive and negative. It tells you the direction of the pattern, whether it's increasing or decreasing. Whereas the trend and seasonal strength is just from 0 to 1. It's saying how strong is the trend and seasonality. It doesn't tell you anything about if the trend is increasing or decreasing, or if the seasonality has a peak in winter or summer. It just tells you if there is trend and seasonality and how strong that pattern is. Another great question. Thank you. Do we have any other questions before we move on? There's plenty of time. Why is strength important? This is useful because otherwise with 300 time series, we couldn't see anything in the data. So remember when I did tourism auto plot with removing the color guide? What can you tell me about the time series here? You can tell me that the most trips that one place has in a quarter is maybe 1,000. There's a lot of places with 0, but really you can't see any patterns here. You can't see if there's trends or seasonality, whereas using features and plotting them is a much clearer overview of the 304 different time series. You can see that holiday travel is more seasonal than other types of travel. So these statistics, these features, are useful ways to summarize the patterns in the data. Does trend have to be straight line or wavy? In this case, because it's using an STL decomposition, remember the trend is able to change over time. So if I go back to the previous slides, see how the trend here out of the STL decomposition is changing over time? This is a nonlinear trend. It's not a straight line through the data. And so this is calculated for the variance of the trend plus the remainder. And so it is allowed to be a nonlinear trend because the localized regression allows it to be. So it's a very powerful technique that works for both linear and nonlinear seasonality and trend. Where am I? This one here. Another great question. Thank you for that. Okay, a few steps back. Difficult to understand what a time series is related to a time series data set. Yeah, so a time series, put simply, is any sequence of numbers over time. So I might have a data set like this. It starts small. So maybe I have a 3, a 6, and then it drops back down to a 5, 4, and this is all over time. So this is a series of numbers over time. So I'm using this to describe a time series. It's just one set of numbers over time. A time series data set is a Sybil. In this data set, time series data set, I have 304 different time series. I've got lots of data packed into this one data set. So there's a very subtle difference between time series and time series data sets, where time series refers to just a single time series, whereas the data set contains everything. Thank you for that one. Looking at the data, the trend strength is not sorted. How are we sure it's not just selecting the first row and not the most trendy? So there's a few ways you could look at this, and it's collecting the most trendy because I'm weighting it by, see this weight argument for ordering. If I just used top N, top N3, then I will in fact get just the first 3 rows. And this isn't the most trendy. So you're right, if I arranged it by trend strength, decreasing, then the top 3 here is the most trendy. So 628, 548, 546. Perhaps not. Oh, it automatically chooses one. Okay, so it would be slice max for the alternative that I was thinking of. Okay, well, the top N function will always choose sorting by something. And if I set top N3, it's defaulting to the ACF. But because I'm telling it to sort by trend strength, this is giving me the top 3 trend. But you're right, if I took the first 3 rows after sorting, I get the same results as top N sorted by trend strength. So you can see 934, 864, 848, the exact same results here, just a slightly different order from top N. But of course, if I did this without sorting the data, then I would just get in order of the original data set, which isn't any pattern with trend or seasonality. So the code that I've shared is correct with top N, but you do need to specify what variable it's sorted by. Okay, where can you get the notes and the code? That's all available on the website here. So you can find all of the recordings and the code from this workshop on the schedule. If you go to day 2 or whatever day you want to see and click on resources, you'll be able to find the recording. We'll put this year's recording up as soon as it's available. And you can find all of the code that I've shared at this link here. I will once again put the code from today in the chat. This one here, in case you needed to catch up. Any other questions before we move on? Okay, so to check, it's currently 10:15. We've got another hour, is that right?
That's correct, yeah.
Excellent, thank you. Time zones are not easy. Okay, so back to these exercises. So we're able to use these features to pull out the most interesting time series from a large collection, but it's most useful to produce an overview plot of all of the patterns in the dataset. For for example, looking at trend and seasonality. But there are more than just STL features that we can consider. If you remember last week, we looked at the ACF plot as well. So if I look at the ACF again, let's look at it for our most trendy time series. So what is the ACF plot of these? I could calculate the ACF of trips and then autoplot it. This same code that we saw yesterday can be mixed around with other code that we're sharing today. So you might take the decomposition, extract the components, and then calculate and plot the ACF. In this case, I've calculated the most trendy time series, and I'm going to calculate the ACF and plot it. Okay, a bit of a quiz since we've got the time. You don't need to set up an actual poll, but I would like to see some answers in the chat. What does this first plot show us? Do you remember how to interpret the ACF from yesterday? What patterns do we have in the business travel to Western Australia? So you can see in the ACF, we have a slow decay. Does this mean we have a trend, a seasonality, a cycle? What pattern does a slow decay in the ACF correspond to? Okay, I see a few answers rolling in now. You're correct. So a slow decay is corresponding to a trend in the data. And looking at lag 4, because this is quarterly data, if we look at lag 4, we don't see that scalloping pattern. So there's probably not much seasonality in this time series. Excellent. I see lots more answers coming in now. So no seasonality, all positive, meaning we have a trend. Very good. What about Western Australia holiday in the ACF? What does this plot show us in trend, seasonality, and cycles? Yeah, that's very good. So you're all right here. This holiday travel in quarter 4 has seasonality. Now, it's not a cycle because you can see it's very definitive that it's always every 4 quarters that the pattern repeats. If it was a cycle, it would be less consistent than seasonality, meaning sometimes it might be every 3 or 4. It varies from year to year. Whereas this one is definitely seasonality. You can also see that there's no trend because we don't have a slow decay. In this case, it's immediately decayed to 0. So there's very little trend, if any, in this data set. But this is odd because we've got the most trendy, and it just means that in this data set, there's not much trend at all across all of the data. Remember, the maximum trend wasn't very strong. But these metrics are only summaries. They don't really tell the entire picture. Looking at more visualizations of the data, we'll get a clearer view of the patterns. Okay, last one, Victorian holiday travel to Melbourne. What does this ACF show us? Okay, a few different answers coming into this one. This one's perhaps a bit more tricky. I'm seeing trend, cycle, trend no seasonality, some seasonality. A lot of people saying trend. So the correct answer for this one is that yes, there is a trend. Of course, it's slowly decaying, just like the first one. But this one also has a little bit of seasonality. You might have guessed that because it's holiday travel, and holiday travel was very seasonal. But you can see in the ACF that at lag 4, 8, 12, and 16, the ACF increases just a little bit. Not so much for 12, but it's very clear in 16. Now, it's not cyclical either because it's the increase at lag 4, 8, 12, 16 is pretty consistent. But that one's pretty difficult to see because there's not much seasonality in this data set. There's only a slight seasonality. Now, going back to the plot of this data, hopefully we can see what we identified. So that first plot that we looked at was, I believe, the business travel to Western Australia. So that's this red line here. You can see that there's a trend, but there isn't seasonality. See how there's no seasonality? Whereas the second plot we looked at with Western Australian holiday, you can see that there's not much trend. Maybe there's a slight trend. But the main feature here is the seasonality. And Melbourne Victorian holidays has a definite trend and maybe a bit of seasonality, but if it is, it's incredibly weak. So I would also say to everyone that just said trend without seasonality, I would say that you're also right based on the this plot here. But the ACF was able to reveal a very, very slight seasonal pattern that wasn't very obvious in this plot. So we can see that using the ACF is a useful indicator of patterns in the data. And what we can use is those autocorrelations as features as well. So in addition to the STL features like trend strength and seasonal strength, we can use ACF features for the autocorrelation at lag 1, autocorrelation at lag 10, the autocorrelation at lag 1 if I've transformed the data using a difference, and various other summary calculations of autocorrelations. And you can compute heaps of these, and they all give a different view of what the data contains. Now, these aren't as interpretable as the trend strength and the seasonal strength, but they help identify different clusters of similar time series. I think we'll probably finish a little bit early today because there seems to be just one more topic. So there'll be plenty of time for questions if you have them. Dimension reduction for features. This is another powerful technique that we can use with features, the feature space, because often, just like we had a problem with computing having too much time series data, we can calculate a lot of different features to see different angles of the data. And when we have a lot of variables, it's a good idea to use dimension reduction to get the most variance from the most variables. So here's some code which calculates all of the features that we possibly can from the feasts package. Now this is the package that we use for plotting the data, like using the season plot and sub-series plot, but it also includes all of the features like Guerrero's method, STL features, and ACF features. It also has a few others, I forget exactly which. Let's have a look. We can look at the PACF that we'll learn later this week, intermittent time series if you've got a lot of zeros and gaps in the data, spectral entropy, There's a lot of different features that exist in this package. So I'll copy this one into the chat as well for you to try out. There you go. Now, some of these features do take some time to calculate. There's quite a few models that are used to estimate these features, just like we did with the STL decomposition model, in order to calculate the trend strength and seasonal strength. Some of the other features in this data set, in this package, require modeling. So tourism features is just finished now. And you can see that I now have 51 different columns. 3 of them are the identifying column, my key variables. So I've calculated 48 different features from the data. And there's a question here, is this everything we've done so far in one command? Yes, so this is all of the features that we've seen so far. So we can pull out tourism features, select Guerrero. Oh, it didn't calculate Guerrero actually. Guerrero is not considered a feature, it's more of a statistic. We can calculate the seasonal strength, or obtain the seasonal strength for each time series. You've also got the trend strength. The ACF that we saw on the slide. All of these features that exist, including more, like the spectral entropy, is a useful one. It informs how much information exists in the time series, how forecastable it is. So we have lots of different things that we could use to look at the data, but there's far too many to look all at once. But really, we just want to see which time series are similar to other time series. We want to cluster similar time series so that we don't have to look at hundreds of them. We can just look at a few from each cluster. And thanks for copying the code across into the chat. That's really helpful. So you might have heard of principal components before. Has anyone heard of principal components or dimension reduction before? It's a very common technique for summarizing lots of data in cross-sectional settings. Excellent. I see most of you saying yes. Excellent. So the exact same principal components, and in fact, if you used R for principal components, you've probably used this function before. Principal components can be used to visualize time series features as well, because the features are summarizing over time. We no longer have a time series. We've just got a cross-sectional data set summarizing the overall patterns in each time series. So I'll copy this code into the chat as well, and if someone can put it in the Q&A for those that can't copy it. Here I'm taking my features that I've calculated earlier. I'm going to remove the key columns because they're not numeric. To do principal components, you need numeric variables. Another nice way to do this is select where is .numeric. This will also remove the categorical variables that exist in the dataset. And you can see I've got all 48 of my time series features that I'll use for principal components. And then I calculate the principal components and add them to my original tourism dataset, my features dataset, with the augment function. So perhaps before the augment, you've probably seen this principal components output before. So these are my coefficients for each of my principal components of the rotation, and the deviance, the standard deviation, which tells you how much variation has been explained by each principal component. The augment function just adds it to the original data set with the trend strength and seasonal strength. So now, in addition to my features, I've got my principal components in the same data set. And with principal components, it's a good idea to plot them. So here I can create a scatter plot between the first two principal components, because the first two principal components explain the most variation. And that's this plot here. And you can see that there's two main directions where the data goes. So there's two main differences where the time series can vary. And there's one big outlier. This time series here doesn't look like any of the others in the first two principal components. Let's add some extra things to this plot to try and better understand exactly why we've got these two directions. So maybe let's add a color for the purpose of travel, whether it was a holiday or business. And you can see pretty quickly that the holiday travel forms a pretty big cluster in this direction. So a lot of these holiday time series look very similar, and a similar forecasting model could be used to forecast them. You can also see some layers here. So the other time series is the lowest, then followed by business, and then in purple, a bit more spread out, is visiting. So the visiting time series in purple are far more different from one another compared to the other, which is more closely related to each other. They look more similar. We could also plot by state. So here I have added the color to be state. And in this case, there doesn't seem to be much relationship between the clusters of time series and the state. But when I plot by purpose, as I showed you in R, you can see that there's a very clear clustering of holiday travel separate from the other travel. And we can, of course, find some outliers. So how would we have a look at these outliers? I want to look at the time series for each of these 4 time series and see what makes them so different from the others. How would I do that? It's very similar to when I looked at the maximum seasonality and the maximum trend. Well, you can see all of these outliers have a fitted principal component 1 greater than 10. See that line? At 10, they're all larger than 10. So I can match up the time series that have principal component 1 greater than 10 in order to find these outliers. So take my principal components. We can filter the fitted PC1 to be greater than 10, and we get the 4 time series that are the outlying time series. These time series don't look like the other ones. So now I'm going to call these tourism outliers. And I can use the same semi-join code that I did before in order to plot them. So I take my tourism dataset, which has all 304 different time series. I semi-join tourism outliers to keep only the tourism dataset time series, which were outliers. So now I have just 4 different time series all of them are matching these outliers in the principal components. So this one, and these two. Finally, we can plot these time series. And you can see the time plot of these. And these ones are a little odd because this green one is incredibly seasonal. This is more seasonal than any time series that we've seen in this dataset. This business one, this one here, is the least seasonal in the dataset. And when you look at other dimensions in principal components, that's this one here, it's the least seasonal. See how it's the lowest in fitted principal components 2. There's other dimensions like ACF and forecastability and all the other 48 different dimensions we looked at, but most of this is seasonality and not seasonality, and trend is the most dominant features. So this is the least seasonal time series, and that's what makes it weird as an odd time series to look at. Now this blue one, holiday travel here, Melbourne Victorian holiday, is strange. See how it's trended up? Almost all of the time series in this dataset are completely flat right until the end, whereas this one has been increasing for the entire time series. That's unlike any other dataset, any other time series in this dataset. And lastly, this holiday one is probably different in different dimensions, not just principal component, not just seasonal strength and trend strength, but probably because it doesn't have much random variation, it's very forecastable. You'll have to have a closer look at the other features to understand why this one is so unique. But at least statistically, using principal components, we can see and isolate the time series that are most unique, even though we couldn't possibly do this by looking at the autoplot all at once. And just by looking at trend strength and seasonal strength isn't enough either. So using all of these features and using principal components, looking for outliers is a very nice technique to spot anything interesting in the data, especially when you've got hundreds of thousands of time series to work with. Okay, so the last one here is an alternative way of doing that same code. We've taken the outliers, this time we've added the time series. It's the same as the semi-join I showed you, and this time it's been faceted by time series, but it's those same 4 time series plotted slightly differently. Okay, any questions on what we've done so far? Okay, thank you again for putting the code in the question and answer for everybody. This question here, can you please explain what does dimension reduction do? Of course. So in this case, we had 48 different features. So let me bring them back. Maybe I can view this data set. So I had region, state, and purpose, but I also calculated the trend strength, the seasonal strength, the peaks and troughs, spiky, linearity, curvature, all of the ACF features. There's a lot of those. I calculated how many times it was running on 0, the proportion of the data that was 0 at the start and the end. Oh, there is Guerrero's method in here as well. It's just prefixed with the word lambda. So I've got lambda here as well that we saw earlier today. I've got various statistical tests for unit roots. I've got various other test statistics, some time varying statistics, entropy, crossing points of 0, or the mean, I should say, flat spots, Hurst coefficients. There's all sorts of different features. And I can't possibly look at all of these at the same time because then I would have to visualize 48 dimensions. And I've only got 2 dimensions to work with here. I've got the y-axis and the x-axis. So to use dimension reduction, to use principal components, or principal component analysis, this takes a linear combination of all of these numeric variables, all of these features, and it arranges them in such a way that the variance is maximized. So it takes the most interesting parts of each coefficient, each feature, and reduces it into a single dimension, principal component 1. And then whatever's left, the most interesting parts go into principal component 2, and then principal component 3, and so on. And then as we get further on to principal component 48, this contains hardly anything interesting. Whereas the Hurst coefficient right at the end of the original feature space is interesting. So the principal components essentially rearranges all of my features in a way that is most interesting in combination to least interesting. And this helps with identifying outliers. You can actually see those coefficients if I look at the principal components here. You can see the first principal component that I was plotting and using for the outliers, 20% of it is simply the trend strength. So it's 0.2 times trend strength. Another 20% of it is the seasonal strength. We don't use the peak very much, we don't use the trough very much, but we are using how linear it is. So if this is linear or curvy, that has a big impact on the first principal component. We're also using the ACF at lag 1 and 10 a lot, the transformed ACF a lot. So we're using all of these different dimensions and summarizing them into just one column of data, principal component 1. And then we plot the first 2 principal components because they're the most interesting principal components in order to see which the overall structure in the data. So we've got principal component 1 and the direction here along principal components 2 as well. And that separates the seasonality with the holiday travel, for example, quite clearly. And there's another question here relating to the coefficients explaining the principal component contribution. That's a different part of the output. So these are the coefficients of the linear combinations that I was talking about before. So there it is. We have trend strength. So the principal component 1 will be equal to 0.206 times trend strength. One moment. Times trend strength plus 0.198 times the seasonal strength, and so on. So it's this linear combination of all of my variables. The amount explained, so the proportion contributing to the model, or the principal component, is described in these standard deviations. So this is the variance of the component. So if I take my principal components, which was this code here, and I'll save this as principal component fit. I think it's just plotting the standard deviations. Now, I think there's a way to normalize this. Maybe there's some instructions in the help here. Maybe I can just plot principal components fit directly. Principal components. Yes. So this is the best way to look at it. So this is actually plotting the variation, the variances from each of the principal components. And you can see almost all of the variance is in the first component, the second component. And then much less of the variance is in the third, fourth, and fifth. So a lot of the variation is explained just in the first two components. And that's a different thing from these coefficients. Instead of the coefficients that I was doing, that is the standard deviations, which is right at the top, this part here. Thanks for the question. And I've explained dimension reduction. Do we have any other questions? That was the last slides that I had for today. We can finish early if there are no further questions.
Okay, shall I pose the...
Yeah, Bahman, did you have any final words? Anything that they should think about before tomorrow?
Not really, apart saying, huge thanks to Mitch for this fantastic 2 days. I don't know if you realize how lucky we are actually to have Mitch with us. So I think we don't have access to the upload functionalities, but I just do it physically like this. I hope everybody is doing it as well. So yeah, you have access. Actually, I don't have access here. So thanks so much, Mitch, for doing this. And of course, everything that we use is, Mitch is the person actually who did this. So without, his work, we wouldn't be able to do all this fantastic work. But, having him is just a gift, really. So thank you so much, Mitch, for doing this.
Too kind, Bahman. We're also very fortunate, of course, to have Bahman, and you'll see just how good he is at teaching for the rest of the week. I will also be seeing you tomorrow. I'll be doing my last session on the basics of forecasting. So you've got that to look forward to tomorrow. I'll be doing some benchmark forecasting models and describing what forecasting is conceptually. And then for the rest of the week, Bahman will be taking you through all of the more advanced models. So Professor Bahman uses a lot of these models in his research and his industry work, solving a lot of big problems around the world. And he'll be talking through exponential smoothing, ARIMA, and accuracy evaluation. So an exciting few more days to come. And I hope to see you for the last time teaching you tomorrow, and enjoy the rest of your AFRICAST workshop. Thank you, everyone. We'll end it.